we live? Yes. All right. Good afternoon, world. How's everyone doing? I believe we are live on the Zoom call, and I believe we're also live on YouTube right now. Okay, so we're still a few minutes earlier, so we're going to wait a little bit for people to join, and then we will start at past 2 or 3 minutes after the time. Okay. All right. Hey, Xiaoxi, how are you doing, sir?
I'm good. I'm good. I guess I probably have to change my background. This is for another class. This is for another class TA work.
Xiaoxi is the head teaching fellow of the class this semester.
Great. Hi, Shashi. How you doing?
Hi, nice to meet you. Nice to meet you. Yeah. See you in a bit.
Things are going well here.
All right. This is 180.
Okay, I think. Are you co-host of the call, Xiaoxi? You are, right? Mhm.
Yes, I am.
Okay, that's good. In case something happens.
Do you set a password for this meeting, or are we still using the waiting room?
It's no, there's no waiting room. There's a password, but which is embedded in the link that students have.
Okay. Yeah.
Yeah, it's under control. Don't worry.
Jose, one thing I might just quickly mention is the internet here in Melbourne is quite good, but every now and again the upload will drop out for 5 seconds or so. So if I do drop out, it's no reason for don't be too scared. I'll be back. It'll just take about 5 seconds of awkward delay.
Is that a well-known problem in Melbourne?
It seems to be happening to a few people. Yeah, I guess everybody's on the internet, and maybe it just gets throttled every now and again.
Interesting.
But hopefully it's fine.
Okay, we're going to wait for a couple more minutes, and then we're going to start. I see there's actually quite a few people following on YouTube right now. All right, I think we can probably get started. All righty. Good afternoon, good morning, good evening, wherever you're calling from. Good morning, William, he's calling from Melbourne, 8 a.m. right there, I think. Thank you very much for waking up to join us this afternoon. I am very happy to announce or to open up the first in the lecture of guest lecture series on the class here, Introduction to Computational Design, GSD-6338. This lecture is going to be a hybrid model, so we're going to be, as you already know, we're going to be having this lecture here on a Zoom call, which is going to be joined by participants of the class currently and other students from the GSD community. But we're also streaming this lecture real time right now on YouTube as well. So people are welcome to join from whatever they want. And the way we're going to conduct this lecture is that the lecture is going to take roughly about 45 minutes. William will be sharing some of their work with us this afternoon, and then we will open it up to Q&A, which will be coming from the Zoom call. So people in the Zoom call will be welcome to open up their video and their microphone and ask questions. People are welcome also as well to post their questions on the chat, and maybe I can broadcast them to William. And then also participants who are watching this lecture right now from YouTube are welcome to post questions or comments on the chat, which I am currently monitoring, and I will be happy to broadcast some of those questions to William. So anybody who is connected right now will have the opportunity to jump in and to interact. And without further ado, I would like to introduce Gwyllim Jahn, who is here speaking tonight, representing Fologram. Fologram is, he is one of the leaders of Fologram, which is a design studio based in Melbourne. I was hoping they would accept my invitation to come and talk because I've been following their work for many years already. And I think it's a really great example of a design practice that is combining modern, high-end, state-of-the-art architectural practices with technological frameworks and computation that they're developing to make their projects possible. They most recently won a competition to build a pavilion in the Tallinn Architecture Biennial, which is the image that we're seeing here as the cover of the lecture. And on top of that, they have developed a lot of a full-fledged technology framework for designing architecture in tandemship with physical devices such as mobile phones, virtual headsets, and to connect them to the typical workflows that we use in architectural design, such as Rhino, Grasshopper, and all those things we're all used to. I think it's an amazing work that they're doing, and that's why I'm very happy and excited to welcome them to open this series this year. And without further ado, I'm going to pass it on to you, William. I'm going to stop sharing, and you can take over.
Thanks so much for that introduction, Jose. Can everybody see the screen? All good?
Yes.
Actually, I'm just gonna double check I got that exactly right. Yep, all good. Okay, so yeah, and this will be a fairly rapid fire 45 minutes. This lecture, I've done the typical thing where you try to condense an hour lecture down into 45 minutes or so. But my hope is that I can give you a little bit of background on what we do at Fologram. Fologram is a kind of a hybrid between a tech startup and a design research practice. Our design practice is mostly involved in eating our own dog food and using the design software that we develop to prove out new use cases for mixed reality in architecture. We're especially interested in Fologram in using mixed reality to improve skills, to leverage intuition, and to facilitate bespoke design in new ways. So we're not necessarily interested in, let's say, improving efficiencies, making it cheaper to build conventional buildings. What we're really interested in doing is facilitating more ambitious experimental architectural projects. All right. So I'm hoping to use this talk to explore the background and context that motivated us to start Fologram, to discuss our design software with you and explain how it works, and to share a bit about what we've learned from around 4 years of designing and making with mixed reality technologies. I think it's also important to speculate very quickly on how the impact that these technologies will have on the future of the built environment, and to try to position this work within the kind of the context of computer-aided design and automated manufacturing. I think Fologram definitely takes a polemical position with regard to this context. So you may be aware that there's been enormous capital investments recently by companies like Katera in industrialized construction processes, and these are a glimpse of the future of the design and construction industry. And the idea is that by owning and standardizing and automating the entire production chain, they can achieve more precise, cheaper, repeatable, and faster production of buildings. The thing is that in this potential future, the role of the architect is going to become more and more that of a specifier. So you'll select modules and finishes from a standardized kit of modules and finishes. So even though a robotic arm is a fairly flexible tool, programming these robotic arms is not something that's necessarily as flexible. They tend to be set up to repeat the same process over and over and over again, as we've seen for a long time in automotive manufacturing. And the same kinds of things are going to happen in architecture. It's going to reduce the degree to which buildings are bespoke manufactured objects. What we want to do is to develop a hybrid approach to industrialized construction, which benefits from the efficiencies of digital processes while maximizing human design agency. So you might think about this as, something like mass bespoke construction rather than mass customization or mass production. The goal is to broaden rather than narrow the spectrum of possible designs and the limits of what and how we build. So to give you a sense of what this kind of mass bespoke design could potentially look like, and to provide a few sort of overarching, aesthetic predispositions that inform a lot of our work, I wanted to share this image. This is an image by a sculptor called Lucy Irvine. She's based in Canberra in Australia. And I like showing this work because it speaks to this idea of like an alternative to the current trend of automating the production of objects in favor of models of production which are just craft-based and slow. So like the slow food movement and the romantics, I guess, at Fologram, we're pretty interested in traditional craft, on drawing on characteristics of local ecosystems and regional expertise, in challenging the need for standardized industrialized processes, and generally just taking a kind of an idealistic disposition towards design quality rather than quantity. And I'm kind of fascinated by this sort of forms and characteristics that emerge from this craft-based practices of just negotiating with material over time. Lucy Irvine's work does this fantastically well. And this is a sculpture which looks like it's been made with some sort of computational process, but it's actually incredibly analog. It's produced just by weaving this irrigation pipe around itself over time, and there's this sort of negotiation between the sensibility of the designer and the behavior of the material that produces this sort of complexity in the final result. And these sorts of forms are actually incredibly difficult to digitally model. You need a kind of this feedback with the material in order to make them. And because they're so hard to digitally model, they're also kind of hard to automate the production of. I'm also kind of interested in how parallel processes of designing and making, this kind of intuitive engagement with material to produce form, can be scaled, so to speak. So in the same way that modular design gets scaled to industrialized construction in factories, what would architecture look like if it was just as feasible to produce these forms like Lucy Irvine's or like this project by Jason Payne that you see here, as it was to produce these kind of repeated modular building constructions. I actually started a PhD to explore this idea of slow robotic fabrication. The PhD's been on hold for the last 3 years or so since we started Fologram, but the idea was to explore autonomous robotic systems that would be optimized for observation and gradual action rather than for speed, for flexibility rather than for repeatability, and for nuance rather than perfect precision. So definitely not typically what you see automated manufacturing systems being used for. To explore these ideas, and those ideas they've kind of continued, like the initial idea with the PhD was to explore them using robotic fabrication. They've since been explored with mixed reality approaches to making. But in either case, in order to explore ideas of kind of slow processes of making, where you engage with material over time, it became pretty important to kind of build our own design tools, so to speak, that could begin to model some of the processes of material behavior in order to speculate on what sorts of possible architectures might emerge from them. So these are some examples of the kinds of design tools that we work with at Fologram. I mean, this is actually from much earlier than before we started Fologram, but it's the same kind of principle, essentially showing how you can try to model or approximately model material behavior over time, things like erosion, deposition, fluid flow, things like that. And by combining these simple behavioral models, you can produce fairly complex design effects and phenomena in which it's sort of possible to begin speculating on possible architectures that might emerge. The same kind of idea of simulating material behavior over time with digital models in order to speculate on these kinds of intuitive processes of making with materials can be applied at smaller scale. So these are the sorts of projects that we were doing about 3 or 4 years ago, exploring in this case how you might be able to produce the design of a meeting room from inflated blobs of recycled and extruded plastic. So this was a competition proposal. We lost the competition, but the idea was that you'd have a kind of direct relationship between the articulation of material properties, things like where or how much the material is inflated, how much color there is in the material, how dense it is, whether it's extruded onto a lightweight bubble or extruded or impacted into a bubble. All of these things serve very specific like architectural requirements. So you can control distributions of transparency for privacy, you can control the thickness of the structure to produce, to make the structure perform. All of this comes from a kind of a spectrum of material behaviors. We lost this competition because the jury rightly pointed out that the technology just didn't exist to build it. And it couldn't be feasibly built by hand. It was just too dangerous to work with that material. It would have taken too long. The design was too complex. We didn't have any tools for extruding the plastic in this way. And so we rightly lost the competition. And to automate this project, it would have required computer vision, real-time robotic control, tools for controlling how the plastic's created, digital actuators for controlling how it's inflated, all of these kinds of constraints. But something that we do all the time at Fologram and that we were doing as part of this research before we started the company is we're always trying to incrementally shift the limits of what we can build. So typically our tools for thinking about design are capable of producing models or forms or ideas or conceptualizations of structures which we aren't able to build. And we just find that really frustrating. We want the two to converge as much as possible. So with this, this inflated plastic project, we started just working through these problems. So we built real-time control systems for robotic arms that you could control with behavioral models rather than with G-code. So this is an example of the robotic arm using 3 Connect scanners basically to scan extruded polystyrene in real time and decide where to place more material based off the behavior of the material it had already placed. So you have this completely bottom-up process of accumulating material over time. We spent a long time mucking around with developing our own custom tools to put on the end of robots. This is almost like a rite of passage if you're doing anything with architectural robotics. You have to build your own end effectors. These are really fun to make. This was a tool that I made with some students in an elective at RMIT, where we were actuating these CMYK dyes to paint filament before it was extruded, with the idea that you could control digitally the color of the extrusion with quite a high degree of precision. We also built a much larger plastic extruder for in an attempt to do bubble inflation, so simple extruder. But the unique thing about this extruder is you could put custom dies on the end of it. So this is a die for extruding tube with an inlet for a digital pressure regulator. So you can control the amount of pressure that is blown into this tube while it's extruding plastic. And this is what that looks like, you know, just extruding a tube. And because the pressure regulator is digital, you literally are dragging a slider in Grasshopper to change the amount of air pressure that is in this tube. So you're, through a digital model, actuating the physical properties of material. And you could potentially create feedback loops between what the sensors observe, how that material is sort of behaving, and the input to the actuator to control how the material is behaving, and then just fine tune that relationship until you produce desirable effects and it becomes completely automated. This is what you get as in terms of sort of material behaviors working with this extruder. So what we managed to do, this is sort of 4 years ago with this PhD research, is we managed to have a robotic arm essentially be able to see its environment in real time, follow behavioral models to determine where to place material. So it could make some kind of very, very simple but informed judgments about how to respond to what the material was doing in its fabrication environment. And we could essentially tune relationships between what the robot observed or what the sensors observed the material was doing and the instructions that were sent to the actuators to control what that material was doing. The thing is that all of this this work to create these digital systems, what you're trying to do essentially is model a really bad human fabricator. It's just, all of these things are just intuitive for craftspeople to do. It's very easy to observe some material and decide whether to inflate a bubble more or less. It's very easy to decide how to deposit more material on top of the material that's there. But these things are very difficult to describe to autonomous systems. And so when we got our hands on the Hololens, we just intuitively realized that all of these problems had been solved for us. So rather than needing to teach robotics to engage with material to approximate human craftsmanship and intuition, instead we could enhance our own ability to work with digital models and just use analog tools to create objects. So because hands are far more dexterous than human arms, this opened up a ton of new fabrication techniques that would be well beyond what we could easily automate, even with extremely sophisticated computer vision systems. And what you're seeing here in this video is the very first project we ever did with the HoloLens. This was within a couple of days of getting it back in 2017 at RMIT. The design, we just quickly put something together in Rhino. And the idea was, can we build something which is fairly complex formally? It's this kind of blob with some holes in it. But could we build it from a really uneven material? So could we build it by just using hot glue and river pebbles and follow a holographic guide to roughly form those stones into the form of this digital model? So because the Rhino model, basically Cam made some software for streaming Rhino models to the HoloLens in real time. That let us very, very quickly experiment with different ways of representing that digital object so that we could fabricate it. So we were able to try things like showing surface contours or showing a point cloud of the model, showing normals as colors or splitting the models into strips until we could identify what was easiest to build from. Basically, when you're working with holographic guides for fabrication, just having a constant reference to the finished form of a project and the design intent of the project eliminates the need for a ton of design rationalization. So you can iterate, you can go through a sort of design to fabrication feedback loop far quicker than you can with just about any other design to production process, especially working from 2D drawings. So digital models in this case can be used as just very approximate guides, and you can leave up a lot of decision making to the intuition of the fabricator. You typically don't need to rationalize things into 2D parts because they're no more difficult to work with than just arbitrary 3D parts. And it typically massively reduces the learning curve for students because teaching rationalization for fabrication is actually quite an involved process. It means also that you eliminate this sort of logistical complexity when you're fabricating things. So this is a still image from a workshop that Roland and Cam ran a few years ago. It's a bunch of robotically bent rods that are assembled into a pavilion. So the fabrication of parts is automated, but often with these sorts of projects where there's some aspect of digital fabrication in the production of them, there's a sort of a hidden massive amount of work, which is just providing the 2D instructions for human assembly teams to put these digitally fabricated parts together. And typically the assembly takes far longer than the digital production. By contrast, working from holographic design models, it tends to invert the this kind of problem space of fabricating complex designs. So the way that it does this is that it makes it simple to build very complex designs approximately using a holographic guide. With traditional and digital fabrication, complexity is usually all or nothing. You have an end product that is exact, but difficult to get exact. And if it isn't exact, if you make a small mistake somewhere, often the whole piece fails. If any one thing is wrong, you can't easily manage it. To give an example of what I mean by this sort of spectrum of approximately making complex designs, this is one of the first structures that we built from building scale materials with the Hololens. It's from 10mm square steel bar. And this is the digital model that we tried to build, and it's a sketch. It took about 20 minutes to model this in Rhino. And the reason that it was so quick to model is because there's no rationalization. So each one of the parts in this model is unique. They intersect with one another. They're just sort of arbitrarily drawn in space. Really all that's trying to happen here is to capture some design intent. So to model a kind of a shape for a top of a chair and to express a possible sort of design language for the structure of the chair, that's it. It's just like a sketch. And then we were able to build this in about 7 hours using an oxytorch, like you see here, just to heat that material in situ and bend it until it overlapped with the hologram that we were looking at in exactly the same place. That means you don't have any measurements, you don't have any templates, you don't have any drawings, you don't have any jigs. Everything's just done working with material, trying to form it until it matches the holographic guide. You might have noticed though that these two models, they're not exactly the same. And that's because when we were fabricating it, we were able to make kind of intelligent and intuitive trade-offs between the precision that we were working to, how closely we matched the digital model, and the fabrication time. So we were trying to do this in under a day. And it meant that because the digital model was just a sketch, we didn't always need to follow it exactly. You might change where a part was very slightly in order to try to match the design intent, but make something much easier to build. So this object is actually deliberately imprecise. It's thinking about the idea of tolerance quite differently to how architects and fabricators typically think about tolerance. And instead it's prioritizing capturing design intent. Like the design intent is what is important. And actually, there's also a kind of a spectrum here. You can make things slowly and precisely if you need to. But it's about realizing the design intent as efficiently as possible and enabling fabricators to use their craft skill to do that. So this idea of building from holographic guides is definitely not new. We love showing this slide in any presentation we give, and it's because this slide is from a paper by 2 engineers at Boeing from the early 1990s who first used the term augmented reality to design a system to help with the manufacturing of aircraft wings. So ever since its conception as a term, AR has always been intended to be used to help with frontline work, specifically to help with making stuff. And the way that it works really effectively is if you're able to show some small amount of digital information within a worker's field of view that helps them do a task that would otherwise be difficult, time-consuming, tedious, etc. So you don't want to immerse them in a completely virtual environment. You just want to provide them with information to help them do what they're trying to do. So almost 30 years later, this idea is now fairly ubiquitous on construction sites. This is an image from a mobile phone AR-based system developed by Trimble for showing basically BIM models on site. And this is used on real construction sites now. So this technology is not far off in the future. It's actually having an impact on how we build now. What Fologram does differently to Trimble is we're not trying to make conventional construction more efficient, which is what this image is trying to do. It's trying to highlight potential clashes or just improve the efficiency of site walks, things like that. We're trying to make more ambitious design more possible. So a different kind of vision and a different goal. The Hololens is what makes our vision very possible now. It's kind of right place, right time. And that's because up until recently, to explore the idea of making a mixed reality, you'd need to build your own custom sensor jigs. You need to buy a very expensive headset and usually customize it. You need to write your own software. It's much like the robotics project that I was showing earlier. Everything's custom and one-off and very difficult. The HoloLens 2, on the other hand, is a off-the-shelf piece of hardware you can buy from Microsoft. It's a self-contained computer. It contains a whole bunch of sensors in it, cameras and infrared depth cameras and things like that, for working out where it is in space so that it can show you digital content quite precisely within physical environments. The thing about the HoloLens, though, is you still need to write software to use it. And most of the creatives who have interesting use cases for the HoloLens aren't software developers. And that's the problem that we're trying to solve, specifically with Fologram. The goal of Fologram is just to reduce the time that it takes for creatives to prototype and evaluate ideas for working in mixed reality. So how we let that actually happen is by helping you build simple mixed reality apps using CAD software. So you connect Rhino and Grasshopper to the HoloLens or mobile phones or Oculus Quest headsets, and you can stream geometry to the mobile phone or headset so you can see it in AR, and you stream your interactions with that geometry, like where you are in space or if you're tapping on the screen or whatever it might be, back into the design environment so that you can use it to trigger changes in your parametric models. This, if you know how to use Rhino and Grasshopper already, this for sure is going to be 10 times faster than any other way to prototype any other mixed reality application. It's just really, really quick. And that's what Fologram's specifically for. It's, if you can make it really, really quick and easy to test any random idea you have about how you might want to use mixed reality for design or making, if you can make it really quick and easy, then you might just try it and you'll learn something. Whereas if there's a big overhead to trying any idea, it just limits the degree to which you can experiment with what's actually kind of fairly new technology. So to give you an example of what I mean by that, you've probably never thought of making a darts game in Grasshopper, or maybe in this course you actually have. I've seen some of the Jose's videos on the lecture series. They look like doing all sorts of interesting things. But it's very possible to use CAD software to build things like darts games. What's missing is the user interface for making that darts game fun to play. So when you put on a HoloLens and you can see your Rhino model in space, the first thing you typically want to do is you want to pick it up and throw it to work out just how kind of real it is. There's nothing preventing you from doing that yourself in Grasshopper using Fologram. The other big advantage of working in mixed reality, besides the sort of natural user interfaces that let you interact with your design models in new ways, is that you get collaboration for free. So there's nothing stopping you connecting as many mobile phones or HoloLens as you like to the same Rhino and Grasshopper models, and all interacting with it in parallel at the same time. So this is a little modeling app we built in Grasshopper. It just basically copy pastes Rhino layers in space. And we've got a couple of mobile phones streaming into that at the same time. Anyone with a mobile phone can connect and place models. It's basically building a little Minecraft app. By making mixed reality super easy to use, it's also possible to help kind of creatives that maybe aren't so digitally savvy engage with the technologies. So this is my partner, actually. She's using mixed reality to create these sorts of sculptural objects, basically using holograms as guides for assembling both the flat pieces of the structure as well as painting the enamel on top of it. Other artists and sculptors are using Fologram to create very, very complex 3D forms that are modeled in VR, actually, in these cases, and then just put together by hand using AR as the fabrication guide. You can use augmented reality to interact with digital simulations. So for doing things like engaging with tensile membranes and things like that at one-to-one to do virtual prototypes of these sorts of physical structures, or controlling robotic arms in real time, being able to kind of, let's say, align mixed reality coordinate space with a robotic coordinate space is super useful for doing things like predicting toolpaths and stuff like that. So a couple of quick projects in the last 15 minutes or so of the lecture to run you through how all of this like background context, thinking, tools are actually being applied. And the first one that I wanted to show is a little bit old now, but it was the first time we tried to use mixed reality for pretty much every single aspect of the design to production process. We had modeled a kind of very complex, tangled sort of steel structure that was intended to be built from bent steel rods during a workshop in Tsinghua in Beijing. And we were going to build it in the kind of undercroft of the architecture school there. And the space was a bit of a mess. There's lots of other workshops happening in the same spot. And so we just walked around with the HoloLens. What you see here is essentially the HoloLens 3D scan of that space so that we could build a point cloud of that workshop environment and just double check that we could do things like we're fabricating pretty large parts. We wanted to make sure we could fit them up the ramp to go weld them together, move them to space for exhibition, all the rest of it. So you can create these kinds of 3D environments of site conditions just by walking around with the headset on. The design itself was also really difficult to understand just on a 2D screen because it's just a whole lot of three-dimensional curves. And so the other thing we did was we'd walk around in the virtual model of the structure and just mark it up by tracing our hand position over time. So you could basically quickly identify where parts weren't joining properly, where we needed to add more parts, where we needed to remove them. And at the same time as I was going around and marking it up, Cam was sitting on a laptop and fixing the digital model at the same time. So it's just an incredibly efficient way of marking up complex structures. To bend all of the parts by hand, we didn't use a robot. We just had a cheap analog bar bender that we brought over in our backpack. And we added a holographic overlay to this bender, as well as a holographic user interface that would just show the students in the workshop exactly how to bend each one of the custom 3D polylines in the design. And it's just a really simple process. So you see a hologram of the bend that you need to make, you line up the physical material with that hologram, and then you bend it and make sure it's still aligning with that bend radius to avoid any kind of twist in the material or anything like that. And very quickly, you develop a real skill and intuition for this way of making. and you're able to react to things like the bender being crappy and twisting the material while you're bending it. You get a sense for the spring back of the material. It's a real craft process. Once we've made all the parts, rather than having a situation like this or like this, where you just have spaghetti everywhere, it's really, really difficult to understand where any particular part goes. Even the as-built thing, while you're making it, it's very, very hard to, stop material from sagging, moving around. We just used a holographic guide for the assembly. So you would fabricate a part, and as soon as you'd finished making it, we had another team of students who would grab that part. They would select it in a holographic model, which would show them where it's supposed to go. And then again, they could use their intuition to weave it through the structure until it overlapped with the hologram that they were seeing of where it should go. So it made what would have been an incredibly difficult process to automate or to follow from 2D drawings extremely simple. So here you see the red part, which we're trying to place, and a simple user interface for stepping through those parts. And all of this is just done in Rhino. We also digitized the structure, but I might skip through this in the interest of time. Basically, it's this idea of being able to trace the physical object. So you take a bunch of sample points, stream those into Rhino and Grasshopper, and then you can recreate the digital thing, or recreate the physical thing, sorry, just from a bunch of digital points. So what is important to show, though, is just the precision that you can get with these processes. So this is the initial digital model before we built it of a bunch of parts. This is where the model deviated from the digital model. So where it's red, you have a lot of deviation. And then that's the digitized version of the as-built model. So it's pretty precise in this case. I think the maximum deviation is around 26 mil and the average was around 16 mil. But we wrote a paper on this, so you can go and check it out if you're interested in it more. We're also interested in using mixed reality for, let's say, more conventional construction. So there's not, that previous project's extremely sculptural. We wanted to see if we could improve the way that, in this case, bricklayers worked in mixed reality. And the way that we did that was really, really simple. So again, you have a very, very simple mixed reality application, which would take a 3D model of a design of a brick wall and just allow the bricklayers to view one course of the brick wall at a time. So wherever they saw the footprint of a brick, they could place a physical brick. Once those two overlapped, they knew it was right. We had explored this quite a bit with foam bricks, which you can just glue together. So very, very fast process. This is from a workshop in Germany. It's a couple of thousand foam bricks glued together in about 4 hours. So we knew the mixed reality approach would work. We just wanted to test if it would also work at full scale. So this is a project with Colin from Albrick in Tasmania, about 600 bricks. This is the digital model, and in a second he'll talk about how it was done.
There isn't a single brick on there that lines up to anything. Every brick is different. This would take you like 2 weeks.
Yeah.
Fine guy, and a lot of that would have to be, made up. Do you know what I mean? You're not going to get it exactly like this would be.
So same interface, you can tap on a button to change the course of bricks you're seeing. It's just showing you the footprint of the brick. So it's like a little wireframe you place the brick into. And it meant they could construct the
So that's all the bricks, right?
Yep.
So see how you are here. That one's good.
Yep.
This one here shows it's got to come round. So just treat that like you do your string line all the way around.
Mm-hmm.
So hit that back.
So that was Colin training an apprentice using this really complex job. And they invented some really interesting ways of building the wall in parallel. Normally it'd have to be done by one really skilled guy, but instead they could have multiple people building it at once. And the precision was really, really good. It was construction site precision on this project using the Hololens. You can see here what they're doing. They're basically adjusting each brick until it fills the digital wireframe that you see. Now, I have to apologize in advance. Just block your ears if you don't like rude language.
I once seen a program on John Lennon, you know, and he reckons every song that he made, he used to get scared that, fuck, I'm going to stop now because I'll never make anything better than that, you know. That's how I'm thinking, fuck, it's time to stop. I'm nervous that I can't make nothing better.
So Colin was pretty happy about that process because it extended what his team was able to do. So rather than one guy doing a pretty tedious job of measuring out where each one of these bricks had to go, instead you could have 3 guys doing the job in parallel. They always had the kind of construction information they needed. They didn't have to worry about getting anything wrong. They could see exactly what the end result was supposed to be like. And so they could concentrate on just doing a really good job. And that's what they're proud of. That's what they're interested in achieving. Another project I wanted to show is the Thailand Pavilion. This is a project that was very collaborative. So the design was completed with myself and Cam from Fologram, Sumin Harm and Igor Pantic from the Bartlett, and James Sully and his team at Format Engineers, as well as a ton of volunteers and friends who helped us realize the project along the way. Now, the idea with the pavilion was to try to use AR to create basically custom jigs and templates for steam bending timber. Normally, this is a really tedious and time-consuming process. And we figured, well, if you've got a hologram showing you exactly how to lay out some formwork, we can probably make it really simple and quick. Again, inverting that kind of feasibility of a complex task and making it really easy. We did a couple of small scale tests in our studio exploring this idea. They worked really well. And so we thought, well, let's just ramp the design complexity up to 100. We'll be able to bend any bit of timber we want. Let's just try to really capitalize on this sort of language of curvature from the steam bent timber. We use a few different materials. We'll build the thing in chunks and it'll end up looking like this. We didn't really expect to win the competition. We just thought it'd be a kind of a cool idea. And we really didn't think about how this thing would actually be realistically built if we did win, to be completely frank. We knew that the AR side of things was going to work pretty well, but we'd never done any steam bending of timber before other than small scale prototypes. So that was a big unknown for us. When it was published on Arc Daily, this project, after we did win it, pretty much all the comments said that can't be built. This is the jury deciding on which project to choose, actually. We really appreciate the jury deciding to support us and force us to go out and figure out how to build it. And because that opportunity in the end was really valuable.
Philip doesn't look very convinced.
Yeah, he doesn't, does he? He's umming and ahhing about it. Though Philip actually, he mentioned, like, in the end, it's a shell. So the engineering side of things is not too bad. It's the controlling the material and avoiding accumulative errors, which is the scary bit. The big challenge with steam bending timber is that you have to deal with spring back, and this is also one of the reasons why it's a kind of a very traditional craft technique. You don't see it a lot with automated approaches to manufacturing. And the first full-scale steam bent strip that we made looked like this. So on the mold, it's the black set of lines. When you take it off the mold after it's dried, it's the red set of lines. So you get a huge amount of spring back. And luckily with AR, like holographic models, you could at least see exactly where the spring back was. So you knew if a part was right or not, whereas even that is typically pretty challenging with conventional construction. We really didn't want to laser cut any parts of the design. We actually didn't have time or budget. The pavilion budget was tiny. And we also, partly because of that reason, we didn't want to use a substructure at all. So the whole structure needed to be a very lightweight shell consisting of parts that were manufactured entirely from stock materials, so we didn't have to laser cut anything. And we needed to solve the problem of spring back. So in the first couple of prototypes we did, we tried making kind of small parts from steam bent timber. This is one of the first ones we made, and you maybe can just make out there's an actual piece of timber underneath this digital model of the timber in the same spot. So you'd have a holographic guide showing you how to lay out the formwork, which ended up being these stands on a false floor. And you would steam bend the timber while you're wearing the HoloLens, and you'd bend it over the formwork so that it matched as closely as possible this hologram of the part. And this first prototype, this is done at Temple University with Andrew Witt, Tim Rusterholz, Chris McAdams, and James Pazzi, as well as a bunch of students. And it was a complete nightmare. We tried to build about a fifth of the pavilion in 2 days. And we just could not control the spring back at all. All the parts were too small. It was hundreds and hundreds of parts we had to make. And the imprecision was just out of control. So even though we could capture some of the formal characteristics of the pavilion, there was no way we were going to be able to scale it up. And the only solution to that problem that we were able to come up with, which ended up being a really great solution, was to make the parts much, much larger. So we ended up working with 12-meter long parts that were steamed and bent in bags. And once we knew that we could do that, we rationalized the design of the pavilion a little bit, mostly just into 12-meter long parts. We made all the parts as long as we possibly could. Had to make sure those parts weren't self-intersecting. There was actually a ton of constraints in terms of the computational modeling for this project, which I might quickly run through. Things like making sure that your digital model of a timber board matched the expected shape of the steam bent timber as closely as possible, because we had to digitally model these connecting brackets. Had to make sure that we weren't modeling anything beyond what we could bend, so minimizing curvature. Had to remove intersections because we weren't laser cutting anything. Everything had to unroll to a straight section of timber, also because we weren't laser cutting anything. Had to avoid putting lap joints in areas of high curvature. Basically, you just have a ton of fabrication constraints that you need to digitally model somehow. And the way that we ended up doing this is by using physics solvers to model all of these fabrication constraints approximately. So what you see here is a digital model before we run the solver, and all of the parts would need to be laser cut. They don't unroll straight. And the physics model is just negotiating between all of these different design constraints. So it's trying to make the parts unroll straight. It's trying to make the timber boards not intersect with one another. It's trying to minimize curvature. It's trying to match our drawn design intent, which are these black curves. So it's this kind of nice hybrid approach between top-down modeling something where you say, I want the timber board to be exactly this shape, and a kind of a bottom-up model which says, well, that shape can't be built, so how about this shape, which is as close to it as we possibly can make. So this was a really interesting computational approach to doing the pavilion. We also had things like visualizing the curvature of each strip while we were laying it up, so we could avoid putting any low-quality timber where the timber was going to bend a lot. In fabricating the brackets, we also had a ton of different constraints we needed to model, and these were also digitally simulated. So you have an approximate digital model of a bracket which doesn't connect to anything and that doesn't unroll straight. And then you have a physics solver which is trying to make that bracket unroll straight. It's trying to make it connect to the boards as efficiently as possible. It's trying to remove bend angles that can't be fabricated. But all of it approximately, like you never actually get any of these constraints perfect, but you get them to within the tolerances of how we were going to build it, which was by hand anyway. So last couple of minutes of the presentation, this is how we did it. So you have a hologram showing you how to bend these 12-meter long strips of timber. Basically, all you're doing is just working as a team to gradually shape these big floppy bits of timber until they match the digital model. The parts and the formwork were really crazy. They were mostly done ad hoc, actually. So you would just show a digital model of the strip, and then you'd work out where to place the formwork from that. So it really, really simplified the amount of digital modeling we had to do. Like literally, you just take a strip from the design model and orient it flat, and that was it. And we did things like we added holographic overlays to bar benders, so you could fabricate all of the brackets by hand. And these are all compound angles, so really, really complex to build otherwise. And we had holograms on site showing us where each of these brackets needed to go in the structure. And that's really important because the whole structure was expected to sag. The parts are super flexible, so even after you steam bend them, when you lay them out on the ground, under their own weight, they just deform again. So they're really, really difficult to build with, like 12-meter long flexible pieces of timber. And you definitely need a holographic guide when you're working with these kinds of materials, just to know whether or not you've got the parts in the right spot. So I guess to summarize, like with this pavilion, we were pretty interested in demonstrating the capacity for formal variation that was facilitated by such a simple production chain and fabrication process. Like every bit of timber is just a board. They're not laser cut into different parts. Every bit of steel is just a length of steel's flat bar. It's not unique either. And yet you can form these into wildly complex shapes using holographic models, and very, very, very cheaply. And the twisting of the strips and a lot of the other kind of aspects of the design language, they're all a result of just how the material behaves. So if you take a plank of timber and you twist it into a 3D or bend it into a 3D curve, it just naturally twists. And so you get all of these kinds of beautiful material effects just from working with that material. It's a lot like the Lucy Irvine sculpture I showed at the start of the presentation. This shows you what the structure's like. Like every single one of these parts is completely floppy and flexible until they all come together with sort of brilliant engineering from format. A couple of pictures of the thing on the site, being inside the pavilion, details, etc. So the last thing that I wanted to flick through just in a couple of minutes, I know I'm a couple of minutes over time here, is just to show you what's coming next. So already we have people using the Hololens on construction sites for doing things like assembling steel frames, really large scale pieces of or basically art installations being assembled with holographic models right now. The bricklayers in Tasmania, they've been working with the Hololens on much larger scale construction sites. So this is the Royal Hobart Hospital. A lot of the bench work in this project was done using mixed reality guides to build just better quality, large scale brickwork at lower risk. The precision of these approaches, at least up to fairly decent scales, maybe 6 meters or so, is within construction tolerances just straight out of the box using the Hololens. And I think as students, you're going to see a lot of pull from industry for working with this technology. And the reason for that is because this technology fundamentally is attractive to industry because it's going to improve their capability, it's going to upskill their team, it's going to improve their ability to collaborate, it's going to reduce the amount of rework they have to do. They're going to get better quality results. They're going to have more certainty they can deliver the jobs on time. As a result, they're going to save time and money. But all of those other things are equally as important. So as designers, we should be starting to think about these new capabilities and what it'll mean for design. All right, time for some questions. If you're interested in using Fologram, you can get the mobile app, it's free. If you want to share design models online, try app.studio. It's also free. And if you want to find any of these videos that I've shared, they're on our Instagram or Vimeo page. So thanks very much.
Wonderful. We don't have a room for applause, but you can see it from the room right now, from the meeting. Thank you very much.
Thanks, everyone.
For those of you who may have joined the call, either here on Zoom or the people who are on YouTube, there's more than 50 people right now watching this on the stream. I'm going to open it up to questions. So if you're typing it on the chat or if you want to intervene, I can also broadcast those questions from the chat on your behalf. But before we open that up, I would like, well, first of all, I would like to thank you tremendously. I think the work is amazing, even better now that I have had the chance to understand more of the insights of what went through to actually put it together. I am extremely fascinated by the paradigm shift, if you will, that you guys have been able to bring to industry, because I've always been a defendant or like an advocate of technology provides new possibilities, right? And as you, just like you, and just like you started the talk with, hey, like this is not about optimizing process. This is not about building faster. This is about enabling new possibilities. This is about opening the design space through technology. This is at the heart of a lot of the work that we try to do here in this class, and it's also a lot of what I really believe that computational design can be helpful for creative people. And what I really want to commend you for is the idea of like, well, instead of keep working with robots and trying to make robots better, and instead of like nailing down more computer vision algorithms, instead of training neural networks to make better path planning so that we can automate things better, I think the notion of bringing the human back in at the center of the fabrication process, instead of trying to replace the human with algorithms, basically, and then make the best of both worlds, make the best of the traditional craft that humans have developed over centuries, which is something that we probably don't want to lose, but just augmenting that craft with digital technology. I think it's pristine as a concept. I'm very fascinated by projects that make that happen in reality, and even more if those projects are available for the rest of the community like us, so that we can enjoy it and we can be creative with them. Such as, for example, all the students in the class who are now using Fologram for their first assignment in the semester, which I think is great. I have a question for you though. When it comes to, because you are bringing humans back at the center of these processes, but you're giving them all this technology, humans who might have this craft that has been developed and that has cost them time and energy to develop, and it's something that they have pride on, right? What situations have you encountered, if I may perhaps offer resistance? That's my assumption. Maybe it's not the truth, but have you ever encountered situations of resistance where craftsmen may have felt threatened by technology replacing them or making them unnecessary? And I wonder if, for example, the examples that you have shown with the Tasmanian bricklayer, if after trying this, he rethought the role of technology and how it could augment his own skills. What are your thoughts, or what have been your experience in this end?
It's a really good question. Basically, if you are a skilled craftsman, those skills are going to be valuable regardless of whether you're working with mixed reality or not. Like typically, I think if you have access to, let's say you're a sculptor with 10,000 hours of experience, you're an expert, and you really understand your tools and the material, and you have a very good ability to conceptualize a 3D form before it's actually realized and materialized as a physical thing. That's the typically characteristics or skills of an expert. By working in mixed reality, what you'll be able to do is a couple of things. One is you would be able to conceptualize a new, like, different kinds of models, digital models, let's say, or complexity that is outside of the realm of what you might typically formally work with, just because of your training or because of the limitations of your experience or whatever it might be. The other is that you're more efficiently able to delegate. So what we found most with craftspeople is that if you're an expert, the thing that's hardest to delegate is that ability to conceptualize the 3D object before it's made. That's extremely hard to describe to somebody else. You need to use drawings. Drawings are difficult to interpret, or you need to use a 3D model. 3D models are difficult to make, and they're also still difficult to interpret. And what mixed reality does is it just enables everyone to get on the same page so that skill transfer is more efficient. So you might have, in the sculpting scenario, You might have somebody who's incredibly skilled at working with a particular tool, but not so good at conceptualizing 3D models. And this just enables that kind of collaboration and skill transfer far more efficiently. On the other end, if you are not an expert at all, you're a complete amateur, like myself with every single project we've done. What it does is it just, let's say, it sort of reduces the learning curve. So by reducing the chance of failure, like if you can always see what the end result of a task is supposed to be, it really, really improves your ability to learn that task. Like you can see all the time whether or not the thing that you're doing is leading to the result that you want. And that's amazing as a teaching tool. It also means that you can iterate much faster. So you're able to, especially if you're a designer maker, you know, you quickly model something and you quickly build it. And then you can go back to quickly modeling something again. Whereas if you have to model something and then rationalize it into a bunch of parts and then send it to a 3D printer and then print it and the print fails and you go back, it's just this slow process. And that was the biggest issue we had with robotics. It was the iteration time was really, really slow. And you very quickly would get entrenched in particular tools and processes and techniques that would become very, very costly to change. Like for instance, after we built that plastic extruder, we just wanted to work with plastic. Like you don't want to go build another end effector, it'd take you months to build. And the advantage of AR is you say, oh, I'm sick of using this tool, I'll just pick up this other one. I'm sick of with this material, I'll pick up something else and try it. And it just, the experimentation changes fundamentally. And I think most people realize that. So I think we've never had anyone ever say they're threatened by this technology. It always produces excitement because everybody can see that those affordances are so immediately kind of like beneficial and just right there. And the real things that people get frustrated by or scared of are not the technology itself, but more let's say the translation of where they see the opportunity to actually doing it. That's the thing that people are scared of. Like they see there's an opportunity there, but they don't quite know how to realize it yet. And that's something we're always trying to improve because not everybody uses Grasshopper. So that's a challenge.
Absolutely. Wonderful. May I ask you, have you tried laying bricks with the Hololens yourself?
Yeah, we have. Well, we've laid a lot of foam bricks. They're easy. And then laying, like working with mortar is really difficult. That's where all the skill comes in. Because everything is in flux, it's dynamic, things move. And you really need to know you need to be able to anticipate how things are going to move in order to work with the holographic information effectively. So yeah, we've tried and we respect the craftspeople as a result.
Amazing. Thank you, William. I'm going to open it up to questions. There's a lot of applause and a lot of wonderful emojis coming in from the YouTube chat. I'm going to open it here first. There are some questions from Kritika. If you want to unmute yourself and perhaps join in.
Yeah, sure. Thank you. And thank you for the wonderful presentation. It was so amazing to see all of these interesting projects. I had a question about the process. I was wondering what inspires you to, choose a particular material, because I think in most of the projects, it seems to be like a permutation and combination where you have some sort of material idea at the back of your mind, and then you explore these different options and experiment that, what should be the final outcome. So if you would just like to throw some light on that.
Yeah, that's a good observation. I think we always start with the material first. Yeah, I think and so we've usually got a hunch about how maybe that material is particularly well suited to a fabrication technique, or maybe it's well suited to a particular way of forming it that then drives the whole project. So great example would be we've done a lot of these rod bent projects just because the material is cheap, it's easy to work with, the tools for forming it are cheap, the holographic instructions are easy to make, and it's easy to digitally model stuff out of polylines. So it's sort of tick, 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 tick. But on the other hand, you end up with things which are wireframes, and so they're not so easy to create enclosure or all of these other sorts of, you know, they're kind of limited, I guess. They don't do everything. And so the idea behind working with the steam bent timber is to try to form something from surface in order to create sort of far more complex architectural effects. There's so many more opportunities for working with materials in ways that we haven't really explored. I mean, working with membranes and textiles and just sheet material generally, I think is there's a lot of opportunities there. We've basically done a lot of steam bending timber, a lot of bending steel, a lot of work with bricks, and everything else is up for grabs. Actually, on the chat, I'll share just a link to a forum. On there you can find there's a bunch of projects that other people have done with the HoloLens, and a lot of those are from way more interesting material systems. So everything from like chainsawing logs that you find in a forest using a HoloLens, through to spraying concrete on fibrous systems, to weaving bamboo, to all sorts of stuff. There's some beautiful projects on there. So yeah, if you're interested in materials, you should find something that tickles your fancy.
So thank you so much.
There is.
Absolutely.
I got a question. So first, thank you so much, Gwyllim, for your presentation and all of these really mind-blowing projects that you showed. Actually, and also I'm very appreciate your idea that's trying to combine the AR as the latest technology together with the human craftsmanship, and trying to exploit the advantage of both of them instead of just totally abandoning the one of them. I think this is a very, very valuable ideas in today's developing of the architecture-related disciplines. And my question is, since as we see in your project, it seems that for many of the works, the AR is actually used as a guideline of a fabrication by human. Have you ever have any project, or you ever try with something like if there is some feedback from the real world fabrication to the digital model or digital systems, and then you get a real-time feedback loop or negotiation between the real world, the real physical world, and your digital model. Not only the digital model, but also possibly some physical engine that can give you feedback to the human being as the information of the fabrication. For example, when your team members, you're trying to use hands to bend your timber or your bamboo strip. You said that sometimes you bend it this way. It seems in position, and then after a period of time, then it's gonna deform. What if we have some material physical simulator engine in your digital random model, and when you bend this way, and if this information captured by your AR device and then feedback to my engine, and then my engine is gonna real-timely calculates the materiality, how much it's gonna deform in this way, and it tell me that okay, you can do this, do this for now, but 5 minutes later it's gonna deform into another shape, so you might not want to do this, so try another way. I think do you think that is possible in the future work? I think that will be more exciting if that is the real thing come up in the future.
Yeah, I think that's a really good idea. There's a few projects on the forum in the link that I shared of people trying to explore that. And we have tested it a little bit. So trying to create this, exactly as you say, a feedback between the actions of the fabricator while making something and the digital model. So the digital model can change what it shows you while you're making something to improve your ability to make it. It's especially useful with subtractive processes of formation, where if you cut away too much of a model, it's not easy to put that material back all the time. Whereas when you're bending things, you overbend it, maybe you can underbend it again a little bit. So you have more adaptability in the fabrication process. I can show you a little video. I didn't include it in the presentation because we didn't quite have enough time, but this is an example of that feedback that we've tried. This is a few years ago now. Now, what we're doing is you're tracking a hot wire cutting tool
Cool.
and streaming so that you know where the marker is. You fix that on the tool, and so you can tell where the hot knife is based off where the marker is, and you can then change the color of the hologram based on the distance of the physical tool to the digital hologram, which is really, really interesting. What we found is it didn't help us to, and this is like a 3-hour little experiment. This is not like days of work or anything. What we found is that process worked really, really well if the digital model that you were trying to fabricate as closely as possible matched how you were fabricating it. So we ended up modeling a design from a series of cuts, and then you could really accurately follow those cuts. And then you actually didn't need the feedback as much. It wasn't as important. But yeah, we have we've tried things like that. It's really, really interesting, and I think most of our sort of community of users are rapidly trying way more interesting things than we have. So it's worth checking out the forum to see what people have been up to. It's exciting.
That's so cool. That is so cyber age thing.
Yeah.
Wonderful. Are there any other questions before I move on?
I had one question. Can you hear me well?
Yes,
Yep.
Benjamin.
I had a question regarding, I come from South America, and in South America, bricklaying is very common, and these complex shapes and assisting bricklayers with technology is fascinating. And I'm just wondering if it would work with a lo-fi, maybe a cardboard box sort of VR with cell phones, as HoloLens might be less common or less accessible to some communities. If you wanted to crowdsource building, maybe people will have some sort of phone that could assist, and sort of what's the lowest technology that this sort of building techniques could be applied with?
Yeah, good question. The short answer is there's no way you could do the bricklaying with anything other than the HoloLens. The longer answer is that's because you need three things. One is you need to be able to, it needs to be hands-free. So if you had a mobile AR app, you'd need to hold the phone in one hand and lay bricks with your other hand, and no bricklayer is going to want to do that. They just won't do it. The other thing is you need depth perception. So the thing about the HoloLens is it streams a different image to each eye, and so you can really easily judge how far away a hologram is from you, and so it makes it easier to work out whether or not you have things in the right physical spot, whether they overlap with the hologram. When you look through a 2D screen, you lose all of the depth perception. You need to kind of trick your brain into thinking where something is, or understanding where something is by moving the phone around. You might have noticed that when you work with the mobile phone, you've got to move it to understand how far things are from you. And then the third thing is you need a lot of precision. So with mobile phones, in that situation where you mentioned, where you could have a Google Cardboard and a mobile phone in there with some, running an AR app or something like that, you wouldn't get the precision, I think, anywhere near enough to be able to actually match the design intent. You could definitely try, but your bricks would be all over the place, most likely. So the HoloLens precision is just, it's really reliable, let's say, up to certain scales. You just put it on, you see the hologram, you place the brick there, the hologram's always in the same spot. And it just it eliminates all the frustration for the bricklayers. And that's really important. If something's frustrating, they just won't use it. So I think Hololens is the way to go, unfortunately. Get a secondhand Hololens one. They're nice and cheap now.
And
Thank you.
technology tends to get cheaper over time. So at some point, it will become more accessible and better in general, for sure.
Definitely.
Maybe like a couple of rapid questions from the chat on YouTube. Abhishek Sharma asks about what do you think the future steps in steam bent timber might be? And I'm going to fuse that with a question from the Grasshopper Tutorials, who's asking whether if the result of the bending wood project, you think there is a structural opportunity using the pressure of the bent pieces, and I quote, for better, weirder construction.
Great questions. I mean, we love sharing the pavilion because the idea was like we'd love it if people just copied that project. Like take the idea of steam bending timber in AR and do more with it, because the using augmented reality to lay out the formwork to steam bend these pieces of timber, it does make that fabrication technique so simple to use. And so there are certainly opportunities for using it for all sorts of things, like everything from boat building to furniture fabrication to doing crazy facades to doing other pavilions to anything you can think of. And there's huge benefits to it as well. Like there's almost no waste in the process. You work with it's a cheap natural material. It's rewarding to work with the material in that way. It's not tedious, painful work. So yeah, I mean, what I would say is there's definitely opportunities for steam bending timber. You could look at like people like Matthias Plesnig are, I'm not sure if you've ever heard of him before, but he is the well-known kind of designer celebrity who works with steam bent timber in their work. And he's also a kind of rhino and grasshopper expert. So maybe that's one place to look for ideas for what could be next. Or you could just look at sort of Art Nouveau, kind of just very sort of expressive sculptural forms from sort of pre-industrial manufacturing, and try to find opportunities there.
Wonderful. And the last one, and I don't want to hog your Friday morning anymore, from One Way is asking about what about AI supported augmented reality and the possibility of making error detection in real time? I'm going to jump on that one and reinforce the idea of like, we have humans and they're great at error detection. So why keep going in the, but I don't want to bias your response. Sorry, Gwyllim.
Yeah, I mean, Fologram has a very specific, let's say, modus operandi for how we work, and that is let's make it really quick to prototype an idea. Like let's find the simplest and fastest way we can explore a design idea, and then let's do that. And so as a result, we haven't looked into machine learning, like augmenting capabilities of humans through those sorts of computer vision techniques, neural networks, etc. There is huge opportunity there, but I think it's kind of outside of what we're interested in. Like the idea would be, I guess, you take an extremely unskilled worker and you enable them to do something that would require a lot of skill. Or, I mean, that's not something that we're interested in. We sort of like the idea of learning and adapting and collaborating. Where I could see artificial intelligence and machine learning or things like that being beneficial would be in facilitating processes of making or designing that would just be flat out impossible without it. So that's where it becomes really interesting to us. So not just difficult, tedious, but completely impossible. Things like being able to see inside of materials, or being able to access, let's say, a huge library of design models or images or textures or whatever instantly at the flick of a finger, being able to instantly 3D scan and share the object you're making with somebody else. So basically telepresence applications, those sorts of things are really exciting. And they're also like far more realistic and achievable than people think. Like I'd be very surprised if in the next 5 years you don't have all sorts of really, really exciting tools being built through a combination of sort of machine learning, augmentation, and AR.
Sounds good. William, thank you very much for spending your Friday morning with us. It was a pleasure. I'm highly impressed by your work. I wish you all the best, and I wish you keep doing a lot of great work so that we can all benefit from it. And looking forward for more coming up from Fologram.
Thanks so much for having me, everyone. It's a real pleasure. Thanks for your questions. They're great.
And thank you very much for everyone who has attended the talk, both here and on YouTube. It was a pleasure. Thank you very much, everyone, and stay tuned for more of this. Have a good evening, morning. Bye.